Let's to continue the work of our section. The following speaker is Oleksandr Stokolos on univalent trinomials. Please.
Yeah. Thank you very much for introduction, and thanks all organizers for letting me participate in this conference. This is my fourth time I participate in this conference, so I will refer to my previous talks, but they are for two reasons, because this talk is a continuation of those two. So if you remember my talks, that you will see, I will repeat some basic facts, but I have to refer to my previous talk as well. So now, what's the departure point? So we consider a class of univalent in a unit DS function. The stellar decomposition started with Z and real A in my talk, as is called the Schlicht function. And one of the basic results from geometric complex analysis is that for any Schlicht function, not necessarily with complex coefficients, the image of the unit disk contains the disk of radius quarter, and the value sharp because of Kirby function who get a value at -1 quarter. And this is the image of the range of Kirby function, and here is 1/4, and here we just have a slit. We remove this portion from the complex plane. Let me say more about Kirby quarter theorem and Bieberbach conjecture. Just briefly to remind you, this is a well-known story, but really dramatic and interesting. So the Bieberbach, both theorems were influenced by Bieberbach function, by Kirby function, and the Bieberbach conjecture says that the coefficients of Schlicht function are bounded by value k, not necessarily real, but complex coefficients. And this is a just fragment of Bieberbach article. And so you see there was a general estimate were proven, and just a really innocent, it's a footnote that perhaps Kn is equal n, and Kn is a boundary for the coefficients. And he didn't make any big deal out of that, but then a race started for this, to prove this estimate. So first of all, it was proven for star-like functions, then Loebner proof for the case third coefficient, then Littlewood prove the general case asymptotically with here factor E, then Dieudonné real coefficients, then Garabedian and Schaeffer fourth coefficients, then Pedersen and Zava sixth coefficients, and then Pedersen and Schiffer fifth coefficient, and then there were some intermediate results until Lee-Debranche gets the full proof in 1985. And let me show you just how the estimates of the coefficient related to Kirby theorem. And this is a very, very beautiful argument. I just want to show you, because each talk is supposed to have some proof, some elements of proof. I don't want you to give my proof, but this is a nice, beautiful proof. And you see why the estimate for the second coefficient is important. So the Bieberbach estimate for the second coefficient is this one, second coefficient less or equal than 1. And now let f be Schlicht function, and gamma is the exceptional value for this function. Then a composition of f over gamma and this function is univalent function, and we can decompose 1 over f of 0 in a Taylor series this way, and then decompose f in this way, in standard way. And when we do this just multiplication of two series, we get the second coefficient like this one. We know that this is a univalent function. Therefore, the absolute value of this coefficient less or equal than 2. Or you can rewrite it in the form that absolute value of gamma greater or equal than this expression. But A2 is a coefficient for another Schlicht function. Therefore, it is less or equal than 2. And we get gamma greater or equal than 1/4, which is a statement of Köbe theorem. Very elegant, very nice, simple proof. And you see how they related the estimate of the coefficient and the estimate for the range of the univalent functions. Two magic polynomials, I mentioned it in my previous talks. One is Safrich polynomial. It's a univalent polynomial of this specific form. And uk minus 1, u is a Chebyshev polynomial, and this is a value at some point. And this is what we call Fourier multipliers. And Brandt polynomials. The polynomial is more complicated. We have this common portion. We have some additional portion when we have derivative of Chebyshev polynomial, which is a new person on the stage, new character. Typically, I haven't seen much. I mean, when the derivative of Chebyshev polynomials were involved, and here surprisingly it pops out. So this is another polynomial, and they are extremal in this case. So if you consider the infimum over all polynomial whose sum is 1, sum of coefficient at the value at -1, it was done by Safrich polynomial. It's interesting that if you just change the normalization and put here the normalization, standard Schlicht normalization, then the value, of course, different, but the extremizer also different at its Bayman polynomial. And this is related to Köbe estimate, Köbe theorem, and which give us an estimate for the radius of Köbe theorem from below. And you see when n is getting larger and larger, this is almost 1. And so it approaches to 1/4. But it's a little bit better than 1/4. So for polynomials, for univalent Schlicht polynomials, Köbe theorem, Köbe estimate is a little bit better than 1/4. And 1/4 is the extremal value for all functions and say for all polynomials. How about odd case? So the odd Köbe function is defined like this one, and this is a range for this function. Here we have two slit domain and empty circle and radius circle for 1/2. And there are a couple famous conjectures. So Littlewood and Pelly show that coefficients are bounded, and they say that no doubt that is just again a footnote. No doubt the true bound is given by a equals 1, like in Köbe function. And then it was a kind of surprise that this is not the case. And Fekete and Sierga proves that some coefficients are a little bit more than 1. And so it's not as beautiful in the regular case. And the best estimate for the constant is 1.17, as far as I know, uniform estimate. And some further development were done by Walter Heyman. How about T-symmetric functions? So Sigur hypothesized the coefficients of T-symmetric Schlicht function as this range, this estimate. And again, it turns out that not the case in general, and Littlewood proves that this is not true for sufficiently large T. And then there are series of results, and the state of art at this day is that for T1, 2, and 3, it is false, this estimate. For T greater or equal than 9, it's valid. But for other T, it's an open, pretty hard, difficult question. And our approaches try to kind of project the situation for the space of univalent polynomials and see maybe we can do something better, because in this t-symmetric case there is no even conjecture meaningful, no kind of constant, no estimates even for the second coefficient, for any coefficients. It's just a desert, absolutely terra incognita. Unfortunately, to symmetrize polynomials, it's not an easy task, because standard symmetrization looks like this one. We raise z to power t and extract t roots. So for univalent function, it works perfectly. But if it's polynomial and you extract a root, it might be not a polynomial. And so the first question, what would be the t-symmetric version of these famous polynomials? And they were introduced in a series of papers by these authors. And for suffrage polynomial, now it looks like this one. So it might be not a unique version for t-symmetric version for suffrage polynomial, but seems to us the most kind of natural way to write what is the t-symmetric version of suffrage polynomial. So here is a strange product, but the secret is this product is a mimic for the coefficients of the t-symmetric Kirby function, and it converges to that function if n goes to infinity. And for Brandt polynomials, we introduce also another the t-symmetric version with the same factor, and here we add t here in this index. And we make a couple of conjectures about this, and let me show just pictures. This is a trisymmetric version of suffrage polynomials. And this is trisymmetric version for Brandt polynomials. You see, they look like univalent, the image of a unit circle under univalent mappings, which is very inspired to us. And we try to prove the univalency in general, but in general it was very difficult. But then it turns out that for trinomials like this, or even more general trinomials, the coefficient region for univalent trinomials were found. But in general case, it's so complicated, it's practically impossible to get anything useful of that. And amazingly is that if you consider not general trinomials like this one, but t-symmetric, t-folded trinomials, so the trinomials of this form with real coefficient, that this region simplifies and looks really nice. So I am proud to show you perhaps the most beautiful pictures in this conference. All pictures I seen before, they're really nice and impressed, but this is the simplest one. So these are domains for the coefficients A and B such that this trinomials is univalent. And for different t, as larger t, a smaller domain is, this is a t equals 1, this is t equals 2, and this is t equals 5. Okay, and they are similar to each other. And so the problem now, if you want to say something about trinomials, is just this is a form of trinomial for suffrage case to check if these points are in that regions and where they are or not. And we have done it, and it turns out that for suffrage polynomial, the points which correspond to suffrage polynomial, the coefficients is sitting in this angle. This is C. And immediately you can realize that any other coefficients are less or equal than the coefficients of suffrage polynomials in this case because this is a point with the largest a and b, right? This value of c. So some additional kind of bypass result were obtained. And for the Brandt polynomials, this is exact form for Brandt polynomials in case of that specific trinomials. The corresponding points turns out to be a point when the tangent line to this region, it just goes at the angle at 45 degrees. And so somehow this is a kind of another critical point. So one was sitting over here. This is suffrage, and one is sitting over there, and this is trinomial which corresponds to Brandt polynomials. So it means that we know we have proved that these trinomials, suffrage version of trinomials and Brandt trinomials, T-symmetrized, T-folded, are univalent, and this is our two papers. For suffrage, same authors. For suffrage polynomial, it was published in Annals of Math Physics, Analysis and Mathematical Physics 2 years ago, and for Brandt, it's in Proceedings, and it's electronically published. I'm not sure if it's already published in print, in a paper form. And a young prodigy, Christina Ganesian, who is currently in Barcelona, she recently posted an archive, like a month ago, maybe less, a paper when she proved the univalence of this suffrage polynomial for n equals 4, which is I'm really very happy to see. And you see, it's important now. Problem is to check if say Brandt polynomials are univalent in case n equals 4. So Christina is working hard, but it's a two different animals, and I hope she will do it. But still the difficult still difficult. The problem of univalency of extremal polynomials. So what the problem is that the polynomials, they are very extremal and let me show you why it is extremal. Because if you look at the image, you see cusps on the boundaries, right? The cusp means that the roots of the derivatives are on the boundary. And we know the root of the derivative cannot be inside the region. So this is a boundary case, and no simple criteria works out. There are kind of dozens of criteria, say Nihari criteria, Dieudonné criteria, many other criteria, which give a sufficient conditions that you can check and see if a function or particular polynomial is univalent. But in the case when you are on the verge of univalency, when the boundary is when the derivative of the roots of derivative are sitting on the boundary, any inaccurate movement can push these roots inside the region, and then you lose the univalency. And so it's really very, very delicate problems, delicate subject. And unfortunately, no kind of advanced mathematics can be applied here. It just, you have to show that the boundary has no self-intersection, no loops. It's a kind of combinatorial tour de force proof. I wish I would know more kind of advanced techniques that could be applied here, some mathematical bulldozers. but I'm unaware. Whatever criteria we try to use, it was useless. So, and this is just n equals 4. And I predict that the next step would be n equals 6, like in the Bieberbach conjecture. In the Bieberbach conjecture, if you remember, I show you, it was like 1, 2, 3, 4, 6, and then 5, and then the general case. So it could be that in this situation, if we get 1, 2, 3, 4, which we already have, the next perhaps should be 6. And if we got 5, I think that we can get the full proof. I hope so. That's it. Thank you for your attention, and glory to Ukrainian people, and peace to country.